Welcome back. This is episode 2 of our computer science podcast, a place where Cambridge AS and A level meets IB, DP, and where curiosity meets clarity. In episode 1, we explored what computer science is and why it matters. Today, we go a level deeper inside the machine itself. Because before we can talk algorithms, databases, networks, or object-oriented programming, we need to understand the foundations, the invisible engine that makes everything else possible. So take a breath, relax, and let's walk together through the world inside your computer. The illusion of complexity. When we look at modern computers, phones, laptops, tablets, they feel impossibly powerful. They draw maps, create movies, train AI, run simulations, and connect continents. But underneath all the magic lies something astonishingly simple. Bits, zeros, ones, on, off, electricity flowing or not flowing. As a computer science student, you learn this in the form of binary representation, logic circuits, Boolean algebra, gate level logic, system fundamentals, hardware basics, and machine operation. Different scenarios, same reality. Every program you have ever used is just switching tiny circuits on and off. Understanding that gives you power, the power to think like a computer scientist. Let's take something simple, the number 5. To you, it's just a digit. To a machine, it's 000000101. Text. Every letter is encoded using standards like ASCII or Unicode. ASCII is short form for American Standard Code for Information Interchange. Images. They are grids of pixels, each with binary codes for color. Videos. Just thousands of images per second, plus sound waves converted into numeric samples. If you've ever wondered how Netflix, TikTok, YouTube compresses videos, or how JPEG actually works, this is where it starts. Binary representation is a gateway to compression, encryption, data transmission, and error detection. And students who master this, whether in DP or Cambridge, gain the ability to understand why systems behave the way they do. Now, let's lift the lid and look under the hood, the CPU. Inside the CPU, 3 major units do most of the heavy lifting. The control unit, which is a conductor of the orchestra. The arithmetic logic unit, where calculations and decisions happen. Registers, tiny high-speed memory locations. Any computer science student would have studied the fetch, decode, execute cycle, line by line. Under this fetch, decode, execute cycle, we explore how the CPU interacts with memory, buses, and peripherals. But here's the message behind the learning. When you understand the CPU, you start to understand performance. You understand why some programs lag, why some code is efficient, why multitasking works, why overclocking is risky. The CPU is not magic, it's predictable, and predictable systems can be mastered. Then we have memory. Memory can be categorized into 3: cache, the lightning fast tiny memory; RAM, fast temporary memory; and secondary storage, slower but permanent. These are not random terms for an exam. These are the highways your programs travel on. Students who understand memory hierarchy write better code, troubleshoot problems faster, and design systems that actually work in the real world. Why does the foundation matter? You might think, do I really need all this? I want to learn AI, apps, robotics, cybersecurity, and everything else you can think about. But the answer is simple. Yes, because you can't build skyscrapers on sand. Every advanced field, machine learning, cloud computing, cryptography, game development, stands on these basics. When you know how the machine works, you don't just use technology, you command it. Here's a simple task for you. Pick any everyday digital object. It can be an image, it can be a sound file, a video clip, or a document, and research how it is represented in binary. What encoding does it use? How much storage does it require? How much changing its resolution or quality affects the file size? This will make you think like a computer scientist. Not what does it look like, but how is it represented? Thank you for listening to episode 2. In the next episode, we'll go deeper and explore on some very beautiful ideas like algorithms, how high-level ideas become machine instructions, and how compilers turn human imagination into executable reality. Until then, stay curious, stay motivated, and keep thinking like a computer scientist.